Hello, good afternoon. So I am Taiji Suzuki. So I'm in the University of Tokyo, and as Hans said, so I'm also affiliated to Riken AIP. I'm a deep learning theory team leader. Okay, so today I'm going to talk about deep learning theory. Okay, yeah. So you have seen a lot of success of deep learning in many applications like AlphaGo and Shogi. So deep learning is very strong. And another example is pattern recognitions. So to get state-of-the-art performances, deep learning is necessary. So without it, it is very, very difficult nowadays. And of course, for the foundation models like large language models and diffusion models, so inside of these models, deep neural network is employed, like transformers and UNet. So yeah, so today's AI, so deep neural network is a very important element. So yeah, so deep learning is a kind of a core of the success of these kind of AI technologies. So, but despite its success in many applications, its theoretical understanding is not completely satisfactory. Okay. Yeah, we want to understand why deep learning works so well in this kind of practice. Okay, so we want to know the principle. So actually, in the literature, there have been many theoretical works to tackle this problem. And so many works have reviewed many interesting aspects of neural networks. However, there are still many things that should be explored. So yeah, we know something, we know many things, but there are also many things that should be explored. Okay. So basically, we want to clarify the principle of deep learning. Okay, so what is the core, the essence of a neural network? Okay, and we want to know, so what is essential to realize a good learning system beyond the neural networks? Okay, so if we can clarify the essence of a good learning systems, maybe so we can construct a new learning systems. So beyond the neural networks. So then I think the deep learning theory is very important for this kind of reasons. Okay, so of course, so the people say that the theory is important. For example, the people in NeurIPS and machine learning conferences. So people say that the theories is very important. And so actually, if you go to the machine learning conferences, you will find many theoretical works on the neural networks. So yeah, so actually it is true, but it is also true for the industries. So actually, so the industry does not want to deploy a system that is a completely black box. Okay, so they don't want to use a system in which we don't know what's going on. So yeah, so that's a very bad situations. So yeah, so people in the industries want to make the deep learning white box as much as possible. So we need a deep learning theories. Yeah, so the relationship between the deep learning and the theory is very similar to the relation between mathematics and physics in like 100 years ago. So yeah, 100 years ago, so we have found many interesting physical observations. Okay? So such an observation could not be explained by the classic Newton's dynamics, okay, Newton's mechanism. Okay, so we have observed many interesting new observations, but there was no theory to explain that. So then the physicists developed new theories, like theory of relativity and quantum mechanisms. And then there appeared some interaction between physics and mathematics, and a new mathematics was developed, like Riemannian geometry and functional analysis were developed stimulated by this kind of physics phenomena. Okay, so the same thing is also happening now in information science and machine learning. Okay, so we are observing many interesting experimental results in the neural networks, but there are not enough theoretical analysis that explains such an interesting phenomena. So then many people are trying to develop new theories to explain such a interesting phenomena. Okay, so yeah, so then so I am one of them. Okay, so many other mathematicians and physicists are coming into this field, and they are developing a very nice, strong theoretical results. So I want to explain some of them today. Okay. So in terms of the theories of deep learning, I think there are many layers from application to foundations. So in the application side, so there could be something like interpretability, or maybe explainability is also on here. Okay, in interpretability, so for each input and an output, we want to give some kind of explanations. Okay, why this neural network recognize this picture as a dog or something like that. So we want to give some interpretation for such input-output relations. So this is also very important. Okay, so the next stage or the next layer of deep learning theory, so a little bit fundamental side is the analysis of each techniques. Okay, so in a deep learning, so there are many techniques like dropout and so for example, many techniques. Like for example, in optimization, so people use Adams, or maybe so people use SUM. So there are many techniques. So we want to give some theoretical justifications why such a technique works. So we give some theoretical justification to each such a technique. Okay. Then a little bit more fundamental side, so there is a principle of deep learning. Okay. So here we don't look at each individual techniques, but we want to clarify the principle rather than clarifying each technique. Okay, why deep learning is somehow better than the shallow method. Okay, so today's topic is not only here. Okay, a little bit more fundamental side, so there is a essence of learning. So here at this level, so we don't need to stick to the deep learning. So we investigate what is the good learning systems. So what is the best learning system? That is the most fundamental learning theory topics. Okay, so today, as I said, today's topic is on here. So I will focus on the principle of deep learning. I will not go much into some individual details of each technique. Okay, so I will consider a little bit more kind of general theories of deep learning. So this is today's topic. Okay, so so it is usually said that in this layers of deep learning theories, there are mainly three topics. So one is the representation ability and the generalization ability, and the third one is optimization ability. I think you have heard these kind of things many times. Okay, in the first one, so representation ability, so we reveal what kind of function can be efficiently approximated by the neural networks. This is a kind of a function approximation theories. Okay. The second one is the generalization abilities. So okay. Now, so suppose that we know a kind of approximation theories of a neural network. Then the next question is, can we obtain such an approximation from finite number of observations? Okay, so we only have a finite observations. But based on such a finite training data, we need to estimate the target functions. So it is a little bit different from the approximation theories. This is our generalization ability. The third one is the optimization theories. Okay, so even though we can show that statistically, even though we can show that a neural network has a potential to estimate something, but it is a little bit different from it is computable or not. So then in these layers, we investigate that topics. Okay. So maybe SGD or gradient descent can find a good solutions that can generalize and also that approximate the target function well. So that is the question here. Okay. So today I will basically talk about these part, so the representability and the optimization ability. I will not go much into the details about generalization abilities. Okay. Yeah, so here are some figures that represents that explains the relationship between these three topics. Representability, so we evaluate how far the neural network model is from the true function. So here is the true function. So then we want to approximate the true function by neural network. So that we measure the distance between the true to some target function and a model of a neural network. So this is a representability. And however, so it is very hard to find this best approximator in the neural network model. So we should find this from the finite number of data points. Then the estimator will deviate around here, around these optimal solutions. So we need to evaluate how large it deviates. So that is generation abilities. Okay. Then optimization theory, so we show the components to this estimator. Okay. So here's an outline. So yeah, anyway, so first I'm going to the representability and generation abilities here. And so the first to start the approximation, the representabilities. So the most important part is the universal approximabilities. Yeah, so I think everybody knows these kind of things. But so this is a very well-known result. So that says that the two-layer neural network can approximate any function with any precision by increasing the number of neurons. So if the neural network is sufficiently large, so then such a neural network can approximate any function. So this is called universal approximators. Of course, to state this in a more mathematically rigorous way, so we should identify what is any function at all, what is any precisions. But usually people consider like the set of the continuous functions or L2 space, and as a metric, so we sometimes we usually consider L infinity norm if the target function is a continuous functions, and maybe so you can consider L2 norm if the target function is in L2. So anyway, so this is a very well-known result from 90s and 80s. Okay, but this is of course very important, and this is a kind of a leading, so guiding the principle in the neural networks. So because of these theories, so just increasing the number of data or just increasing the network size, so we can solve any problem. Okay. So basically this theorem says that the neural network can solve any problems because it can represent any input-output relationships. So yeah, so this is our kind of a so guiding principle in a deep learning literatures. So this is also related, leading to this is also connected to the scaling laws. So just increase the size. But however, so we don't know the more we don't know the more quantitative analysis of approximation errors. Even though we can approximate anything, but we want to know more like quantitative errors of approximations. So then maybe so we can get a much more detailed understanding of the neural networks. So actually, it is known that the kernel method, like a Gaussian kernel, is also a universal approximator. As long as you are using Gaussian kernels, then the kernel method can also approximate any target functions. Okay, so therefore, in that sense, in terms of the universal approximability, so the kernel method and the deep learning are same. So there's no difference. But in practice, so deep learning performs better usually compared with the kernel method. For example, in an image, so for example, in an ImageNet data set, so nowadays neural network outperforms the kernel method much so very well. Okay, so why is it? So our next question is why the neural network is much better than the kernel method, while the kernel method is already our universal approximators. Okay, the difference is coming from the feature analytics. Okay, so here is just a very simple comparison. Okay, it is known that the kernel method can be seen as an infinitely wide neural network, two-layer neural network. Okay, the kernel method is just training the two-layer neural network, but the first layer is fixed. Okay, but only the second layer is trained. So that is what the kernel method is doing. So the interesting thing about the kernel method is that so you can implicitly utilize infinite width network, but by using the so-called kernel tricks, you can skip the computation of the infinite many neurons. That is an interesting thing. But on the other hand, its drawback is that it cannot change the first layer's parameters. It fixes the first layers. So it only trains the second layer's parameters. So because this is just a linear model, okay? But on the other hand, so for the neural network, we can train both the first layer and the second layers. Maybe you think this is just a tiny difference. So this doesn't make any big differences. But this difference makes a huge difference in terms of the approximation errors and generalization abilities. Okay, so first layer is trainable or non-trainable. Okay, so we say this difference as a feature learning. So yeah, neural network can do a feature learning by modifying the first layers. But in the kernel method, they fix the first layer, so it cannot perform the feature learning. Okay, so here is another another viewpoint. Okay, so here's another slide that explains the difference between feature learning, so the method that can perform the feature learning or not. Okay, so we start from, so let us consider very basic models, that is our linear models. This is just linear functions. So we just train this linear combination coefficient alpha j. But in the kernel models, instead of xj, so we use our kind of nonlinear features, phi jx. So here, phi jx is some features. So you can see this is our kind of basis functions. We prepare basis functions, many basis functions, and then take its linear combinations. By doing so, we estimate our target function. That is what the kernel method is doing. But this feature map is fixed. This feature map is fixed. But in a neural network, this basis function is also trainable. So for example, in a two-layer neural networks, we can train the first layers. So then this means that this basis function has some parameters and that can be trained. Of course, you can consider very more deeper networks. So then this part could be much more complicated. But anyway, the critical difference is that this basis function is trainable or not. Okay, so then what happens if we fix the basis functions? I want to explain it in this figures. Okay, as I said, in the kernel method, we fix the basis function like a phi1 and phi2. Of course, you can prepare. Usually we prepare infinitely many basis functions, but just for simplicity, I'm plotting just two basis functions. So then maybe the unit. So radius 1 unit sphere, so unit pole could shape like this in our L2 space. Okay, so we have a phi1 and a phi2. So okay, so we are considering this linear combination of the phi1 and the phi2. So if the norm of alpha is 1, so then it looks like this ellipsoid in our L2 space. Okay, so now suppose that there is a target function on here. To cover these target functions, then we need to make the radius very huge like this, because the model is very distorted ellipsoid. To include these target functions, we need to make the alpha, the parameter very very large. So otherwise, we cannot include the target function in the model. So, but if you use a very huge parameters, so then it is not good for the stability of learnings. So if the norm is large, so then maybe generalization error could be very large. So because it can overfit the data. So then this is not a good situation. But if you can train the basis functions, so then if you fix the one basis function, I mean, if you fix the first layers, maybe it looks like this. The model looks like this. But by tuning the first layers, maybe that can contain the target function like this. So because you can change the basis function. So then the ellipsoid can move. Then with small norm of the coefficient, it can include the target function. So then we can reduce some generalization. So it can be a little more stable to estimate the target function. So yeah, so this is the essence. Okay, so why the feature learning is so important is something like this. Okay, so I want to show some theories to explain this kind of intuitions. Okay, So here is a kind of a comparison between width and depth. So which is better? So shall we increase the width or shall we increase the depth? So there's some comparison, depth and width. Okay, so suppose that we have a neural network with depth L and width W. And we want to represent this neural network by shadow network, which has the depth L prime, okay? Then the question is how large, so how large the width should be of this smaller neural network, the shallower neural network. So it is known that in the worst case, to represent this deep neural network by shallow neural network, the width must be exponentially large. Like width should be L prime times W to the power of L divided by L prime. So if the depth L is 10 times larger than the depth of this shallow network, so then the width should be W to the 10. So it's 10 times larger. So it is W to the 10, so that the power of 10 larger. So this is a huge gap. So this analysis says that so depth has a more exponential efficiency in terms of the representative power. If you increase the depth, then the representative power increase in exponential orders. But the width, in terms of width, the representative power increase only in the polynomial orders. So that is the difference of the width and the depth. So you can see some depth separation here. Okay, so here is another situation. Okay, so, it is a little bit small. So let us consider a so-called balance class. Okay, this is a very well-studied function class. So what is the balance class? So suppose that there is a probability measure pi on a unit spheres. Okay, so then we consider this kind of model. So in the balance class consists of this kind of functions. So here, so sigma is the nonlinear activation function, and sigma W transpose X is the first layers. So then as a second layers parameters, AW, so we use AW. This is a weight of each neurons. Okay, then we take this, we take an average of one neuron with respect to the pi. Pi is a distribution on the W, and so that we suppose the W is on a unit sphere. So I should say, so we employ the ReLU activation as a nonlinear activations. So ReLU is a scaling invariant, so you can restrict the W, the first layers parameter, to the unit spheres. Okay, so because it's scale invariant, so yeah, so W can be restricted to normal 1. Okay, so for each W, so we put the weight AW as the second layer parameters, and then we take their average over the W. Okay, now we assume that, so AW satisfies its L2 norm. So L2 norm with respect to the probability measure pi is bounded. We assume this condition. So, and also the function f in H pi has a norm which is defined by like this. That is basically the norm of AW. So it's a L2 norm of AW is the Baron norm of these functions. Okay. Okay, so now we assume that the target function is included in this Baron class. Then we are trying to approximate this function by a finite width network. Okay, so we use a finite width network where the width is m. So then the approximation error can be bounded by 1 over m. Okay, okay, suppose that you fit a finite width network, and by minimizing the L2 norm between the target function f and the finite width network, so then the achievable approximation error could be 1 over m. So yeah, if you increase the width m, so then the approximation error goes to 0. And the important thing here is that, so there is no dimensionality. So in the exponent, there is no dimensionality. So it is just 1 over m. There's no like 1 over m to the power of d, something like that. There is no d appears here. But if you use a so-called random feature model, so there appears a curve of dimensionalities. So what is the random feature models? In the random feature models, so we randomly choose the first layers parameters. Okay, So here, uj is the first radius parameter. So we don't train the first radius parameter. So we randomly choose the first radius parameter. So then we fix it, and then we only train the second radius parameter. So then the achievable approximation error is lower bounded by 1 over m to the power of 2 over d. Okay, so you see that here is the dimensionality. So if the dimension d is large, then this rateable convergence is very, very slow. In other words, to obtain an epsilon accuracy, m should be very large. So to obtain epsilon accuracy, so m should be like epsilon to the minus the order of d. So basically epsilon to the minus d is required. So you can see that it is an exponential dependency on the dimensionality d. So this is our cause of dimensionality. So as I said, so even in a two-layer neural network, if you are allowed to train the first layer or not, so then there appears this kind of huge difference. Okay? It's not so tiny. So then you can imagine that if you stack the neural network in multiple layers, so then I guess the separation, the difference will be huge. So this is this example particularly shows the importance of a feature learning. Okay. So if you have any questions, so you can stop at any time. Okay. So now, I'm going to a little bit more learning theory type analysis. So in here, so I was talking only about some approximation errors, and I want to explain a little bit more test error analysis here. Okay, so let us consider a classic non-parametric regression problem. Here, the output yi is given by f naught xi plus some observation noise gzi. Okay, now we assume that gzi is coming from some Gaussian noise, the mean 0 and the variance sigma square. But yeah, so any other right tail noise is okay, like sub-Gaussian noise, or maybe so bounded support noise is also okay. But anyway, so noise is a sub-Gaussian noise. And we assume that xi, the input xi is a d-dimensional vectors. And just for simplicity, the xi is coming from the compact support, like a 0, 1 to the d, the unit cube. Yeah. So then we have an n data point from this model. So we observe the n input-output pairs, xi, yi, from I equal 1 to n. And we want to estimate the true function f naught from this n data points. Okay, so you can see that this blue line is the true function f naught, and the black dots represents each observations. So we have the black dots, and then from that black dots, we want to estimate the blue line. So this is what we want to do. Then suppose that we have some estimator f hat. Then as a performance measure of f hat, we employ the mean squared error like this. So if this mean squared error is small, so then that estimator is good. So then we compare the mean squared error between some methods like deep learning and kernel methods, and which one is better. Okay, so this is a very classic result of the bias and variance decompositions. So it is known that in this kind of non-parametric regression problem, we have this bias and variance problem, bias and variance decompositions. So suppose that we obtain some estimator by minimizing the training loss, squared loss, in some model class F, like the neural network model or some the kernel models. So whatever. So for any some function class, so the model F. We take the minimum of the training errors. So we let f hat be the minimizer of this training error. So then the predictive error of f hat, the mean square error of f hat, can be decomposed into variance and bias. Okay? So the variance is just a variance of the model, and the bias is the approximation errors. So that is a model bias. So the model bias shows how far the model is from the target function, if not. Okay, and usually the variance is given by m divided by n. So m is the number of parameters that represents the model f. Okay, so m is the number of parameters to that characterizes our model. And so as I said, an approximation error is the model bias. This is the distance between the target function here and the neural network model, or the model F. So more precisely, so this can be written by like this. Okay, the predictive error is just a mean squared error. The mean squared error is decomposed into the variance and the bias. And the bias is what I said. So that is given by like this. And the variance is basically obtained by log of the covering number divided by sample size n. Okay, so I will explain the covering number. But anyway, so covering number measures the kind of capacity of the model, so the complexity of the model, and the log of the covering number coming in the variance. Okay, so if the model size is large, so then this variance becomes large, but the bias could be small. So there is a bias and a bias trade-off. Okay. Then, so what is the variance? What is the covering number? The definition of a covering number is something like that. Okay, so the covering number of some function class f, so f is some model, is the smallest number of balls with radius epsilon measured by the norm, infinity norm, to cover the function class f. Okay, so this f is the class of, for example, a neural network or some kernel models. And we try to cover this model by epsilon balls. Okay, this is in a function class, so this is a function space. So so this epsilon ball, the radius is measured by the n infinity. Okay? We count how many balls is required to cover the whole space F. That is the covering numbers. Now, of course, if the model is huge, so then the required number of balls to cover this model is huge. So in that sense, the covering number measures the complexity of the model. And under some assumptions, so usually the log of the covering number becomes the number of parameters included in the model. So let us consider very simple situations. So so let us consider just a d-dimensional ball in the Euclidean space. Then please consider to cover this unit ball by epsilon ball. Epsilon ball means that the ball with radius epsilon. So we measure the epsilon by Euclidean norm. Then to cover the Euclidean unit ball by epsilon ball, we need basically 1 over epsilon to the d number of balls. Okay, so this can be easily checked by considering the volume of the each epsilon ball. But so to cover the d-dimensional balls, we need to have 1 over epsilon to the d many balls. So therefore, by taking its log, the log over 1 over epsilon to the d is like d times the log 1 over epsilon. So then for the Euclidean ball, so this log over the covering number becomes d. So basically d times some polylog orders. So that means that the log over the covering number measures the dimension of the model. So then you can see that the number of parameters is coming here. So there's many other exceptions, but this is only the intuitions. Okay, so usually the number of parameters is coming here, m over n, the plus approximation errors. Okay, so therefore, to measure the mean squared error of neural networks, we just needed to calculate the covering number of neural network models. Then we can obtain the predictive error bound. Okay, now we want to apply this kind of a general result to explain the scaling laws. Okay, so you know that these days the large language model follows the scaling law. So that means that you increase the model and you increase the number of data, then the performance goes, performance increases in a power orders. Okay. So this figure shows that in the right-hand side is the training times. I mean, in the training times, at each time you observe the one data point, like SGD. So therefore, the right-hand side can be seen as the number of data points you observed. Okay, so the right-hand side is the sample size. Then the vertical axis is a log of the predictive errors. So you can see there is a linear decrease of the loss in terms in this log plot. That means that log of the predictive error is given by minus some constant alpha times log n, where n is the number of training data that you observed, plus some constant log c. So this is what the scaling law is stating. Okay, so can we explain this from this theorem? Okay, these evaluations. Okay. So I should say that so each line corresponds to each model. Okay, so you fix the model size, then you increase the training data sets, then you obtain one line. Okay, so each line corresponds to each models, and by taking the minimum over all the choice of the models, then you obtain this line. So this is So therefore, this scaling law appears by taking the best model for each data set. Okay, so now let us consider a very easy model. Okay, the true function is just a linear model, like a kernel model. So suppose that we have infinitely many basis functions of phi j from j equal 1 to infinity. And so there is a coefficient alpha j. So we assume that the coefficient alpha j decays so sufficiently rapidly. So I mean, there is a so-called mu j. Like mu j is like a j to the minus a. Mu j is decreasing, and alpha j square should decrease a little bit faster than mu j. And more precisely, we assume that the sum of alpha j square divided by mu j should be bounded. We assume this one. So this means that alpha j square should decrease faster than mu j. So otherwise, this summation would diverge. So that means that alpha j square decrease. So something like j to the minus a minus 1 minus epsilon, where epsilon is arbitrarily small. Okay. So we assume these conditions of the target functions. And we also consider the non-parametric regression settings. So as an estimators, we consider the truncated models, the finite dimensional truncated model. So we truncate this infinite sum up to the m. So we only take the phi 1 to phi m as a basis function. Then we fit its linear combination to the target function. Okay. So that means that the model is like the linear combination of phi j from j equal 1 to m. We fit this model to the target data, so by optimizing the coefficient alpha. Okay, so this is just a least squared estimators. So then we apply this slice, this rough evaluations here. Okay, so remember that the predictive error is given by m over n, so the variance plus the model bias. So now the number of the parameters of this finite truncated model is just m. So the variance is just m over n. Then what is the bias? Through the very simple calculations, the bias can be m to the minus a. Okay, because alpha j is decaying like a j to the minus a minus 1. So by summing up the alpha j square, so you can easily check that the bias is like m to the minus a. Okay, so you can see the clear bias and the variance trade-off. So if you increase m, the variance can be increased and the bias can decrease. By taking the optimal m that balances the bias variance, that is given by m equal n to the 1 over 1 plus a, then you obtain this optimal running rate. So this is the optimal answer. The mean squared error can be upper bounded by n to the minus a over 1 plus a. Okay. So you can notice that by taking a log in both sides, the log of the predictive error is given by minus a over 1 plus a times log n plus some constant. So you can see that this is just a scaling law. Well, yeah, so in more details, so if you take the log in both sides for fixed m, So, okay, so sorry, I go back here. We take the log of both sides of these equations for fixed m, so not just minimizing, just before optimizing the model size m, we take the log of this one. Then, so you obtain this curve, okay? So if you fix the m, so then the predictive errors curve behaves like this. Okay, so it behaves like this. But taking the minimum over all choices of the m's, so you have this scaling law. Okay, so this is what we obtained from this very simple linear models. Okay, now let's go back to what's going on in practice. You have these figures. In these figures, each model size, we have this curve. Okay, so you have these curves. So then by taking the minimum of the model size over all choice of the model size, we have this scaling law. The same thing is also happening here. Yeah, so from the theories, we also have these curves. Okay, so in that sense, the scaling law is not so very surprising. So it is very natural. It can be well explained by the simple linear model. But the non-trivial point is that the same thing also happens for very large neural networks like transformers. So the transformer is very different from linear model, but the transformer also obeys this scaling law. So that is the non-trivial point. But from this the classic analysis, the scaling law is very natural phenomena. So here's some other related papers. Okay, so now, I have considered just a linear model, which is very simple. So now we want to go to the neural networks. Okay, so there are many function classes that are typically considered. So like Baron class, that is explained in the previous slide, and the Hilda class, maybe it's a Sobolev class and the Besov class. So there are many examples. But today I will talk about the Besov class. Okay. Maybe so. Imaizumi-san has already talked about these kind of things. I don't know what he talked about. Yeah. So, but anyway, so if the target function f has some structures, then we can show that the deep neural network can be better than the Kalman method. Like for example, if the target function is a piecewise smooth, then deep can outperform the Kalman methods. And another situation is that the target function is included in the so-called Besov class, Besov space. So then we can also show that the deep is better than Kalman. And another typical situation is that the data is on some low-dimensional structures. Data has some low-dimensional structures. So then again, the deep also outperform the Kalman methods. Okay, so there are many situations. Then, but there are many so this kind of situations. So I will show some kind of a unifying viewpoint why deep is better than the Kalman method in each situations. But anyway, so first I will explain these two situations. Okay. So these two situations corresponds to so more general, more generally, that two situation is corresponding to this kind of situations. Okay. In the first part, so if the true function f is included in a Besov space, it is saying that the true function has a smooth part and a non-smooth part. So they have it has some very different properties in one function. Okay, so for some input x, so then around the x here, the function f deviates very much. It has a high frequency component on here, but for input x around here, the target function is very smooth. So it doesn't have a high frequency component. So this is one typical situation where the deep can be better than the Kalman method. Okay, so another situation is that the target function, the true function, depends only the few directions. The other direction is non-informative. So there is only the few informative directions toward which the true function has some information. So okay, so in these figures, the true function deviates only to these directions. But toward this direction, it is just a constant. So this direction is non-informative. Okay. So yeah, these two situations are very typical settings where the deep is better. So why is it? in the left situations, if you use like a Gaussian kernels, so like a Gaussian kernels, so then in the kernel method, we fix the kernel width, and then we put the Gaussian kernel on the space like this, and then we take the linear combination of them. We take the linear combination of these basis functions to represent the target functions. However, once you fix the kernel functions, then widths cannot be changed depending on the input x. So yeah, so you can change the width of the kernel, but it doesn't depend on the input of the locations. So it should use the same width for all x. So therefore, to approximate the target function around here, so maybe you want to use a smaller bandwidth. So to represent a higher frequency component, so you want to use a smaller bandwidth. But if you employ the smaller Gaussian widths, then you have some trouble to represent the target function around here, because the target function is very smooth around here. So if you fit very small, narrow Gaussian kernel to here, then maybe the fitted function could be deviated like this. So then it's not so good to represent the smooth part. But around here, for the smooth part, maybe you want to use a wider width of Gaussian kernels. So, but in the usual kernel method, you cannot do that. So then there is some inefficiency. But as long as you're using a neural network, it can identify which part is rough and which part is smooth. And it uses, so neural network spend the smaller number of resources, or smaller number of parameters to approximate the target function around here. In terms of the Gaussian, in terms of the kernel method, it uses a wider width around here. And around here, the neural network uses a high frequency components. It uses much more resources, much more parameters to explain the deviated function around here. So then, in other words, it can change the resolution of the models, resolution of the frequency of the model, depending on the locations. Then it can improve the performances. So this is called the adaptivity of a neural network. So for the second situation here, so the situation is much more easier to understand. Okay, so in the intermediate layers, you just neglect these directions. You just make use of the information of the input x toward these directions. You just discard this direction. So then you can reduce the dimensionality, then you can avoid the cause of dimensionality. Okay, so first let's go into the left-hand side setting. Okay, so as I said, so this situation corresponds to Besov space. Okay, so the Hilbert space is defined by like this, and the Sobolev space is defined by like this. In the Sobolev space, we basically the norm of the Sobolev space is defined by the k times differentiation, the LP norm of the k times differentiation. That is the Sobolev norm. The Besov space is a kind of extension of this function class. So its formal definition is given by like this. This is very complicated, so I don't want to go much details of this. So yeah, and I don't have so much time to explain this. So just in intuitions, I only give the intuition of the Besov space. The Besov space has three parameters, S and P and Q, B, S, P, Q, S, P, Q. The important part here is only S and P, so you can neglect the Q. Okay, so the Besov norm of F is roughly speaking explained like this. Okay, so the first term is the LP norm of F, plus the second term is the LP norm of the S times differentiations. So therefore, so if S is large, the function F in the Besov class is a higher order differentiable. That means that the function F is smooth. So the S controls the smoothness. And what is the P? So P controls the uniformity of the smoothness. So if P is infinity, you have a L infinity bound of the S times differentiations. For all input X, the S times derivative should be bounded. So if P is infinity. So therefore, P represents the uniformity of the smoothness. But if P is 1, P is small, so then we only have a bound of the integral of S times the derivatives. So now we are considering just a compact support. So then the integral is a kind of just an average. Okay, so you calculate s times derivative of differentiations, then you take the average over the input x. So maybe at some point, so this differentiation could be very, very large. But if the function f is very smooth outside of such local regions, then the average of the derivative could be small. So therefore, if p is small, if p is small, then at some point the function f can be very roughly deviated. So just the average of the smoothness is bounded is okay. So then p represents the uniformity of the smoothness. Okay. So in that situation, so suppose that the target function f naught is included in a Besov space BSPQ. So then the deep learning achieves this rate of convergence of the mean squared errors. It's after taking the bias and the bias trade-off by choosing the optimal size of the neural network model, then the mean squared error can be bounded by n to the minus 2s over 2s plus t. So you can see that the rate of convergence is characterized by the smoothness s and the dimension of the input d. Okay. So it is well known that this is a minimax optimal rate. So minimax optimal means that, so even though you know very, very good estimators, so even though, okay, so you say that I have the optimal estimators, so this is the strongest estimators. But even though you have such a very good estimators, such an estimator cannot go beyond this rate of convergence. Okay? So because this is a kind of lower bound of the estimation errors. So yeah, so then in that sense, deep learning is somehow optimal. Yeah, so up to constant. Okay. But if you, on the other hand, if you use a kernel method or some linear, more generally linear estimators, and it suffers from suboptimality. So like, let us consider some kernel-rich regressions that can achieve only this rate of convergence. So this is a lower bound of the mean squared error of the kernel-rich estimators. You can see that there is an additional term here. This additional term makes it suboptimal. So this additional term can be large if p is large. P is small. So p can be smaller than 1. So this time 1 over p can be arbitrarily large. So yeah, so if p is small, like p is 1 or something like that, so then this term is basically d, the dimension d. So the rate of convergence becomes very, very small, very slow. So this is coming from the adaptivity. So then, as I said, a neural network has adaptivity, so it can change the resolution of the model depending on the input x. But for the kernel method, it cannot change the resolution depending on the input x. Then you suffer from the suboptimal rate. Okay, so I should give us the definition of the linear estimators. So it is a wide class of the estimators class, wide class of the estimators, including the kernel-rich regressions. So remember that the kernel-rich regression can be written by like this. It is linear to the output y. So we have observations xi, y from y equal 1 to n. So you have an output y1 to yn. So then this estimator is linear to the output y. So then we call that estimator is a linear estimator. Yeah. So there are many other examples of linear estimators. Okay. So one example is the Sieve estimators and Nadaraya-Watson estimators, K-nearest neighbor estimators. So they are included in the class of linear estimators. So you can see that Nadaraya-Watson is a linear estimator. But anyway, so for any estimators, including linear estimators, it suffers from this suboptimal rate. Okay. Okay, so yeah, why this difference is coming? So as I said, this is coming from the adaptivity of a neural network. More precisely, so neural network has some connection to the sparse estimation. So actually, the function f in a Besov class admits a sparse expansion using the wavelet basis functions. Okay, so function f has this wavelet decompositions. So phi k is a so-called wavelet basis functions. And so it is known that with a function f in a Besov class, the coefficient alpha can be sparse. That means that the small number of alpha, the small number of coefficients are large, and other coefficients are very, very small. So here is one example of the wavelet basis functions. So okay, so this how to say triangle-shaped basis function is just one example of the wavelet basis. So in a wavelet basis functions, wavelet basis systems, we put this basis function uniformly on the space, and so at some at this resolutions, we put this basis function on the space like this, and after that we increase the resolutions, so 2 times. So I mean, so we shrink the width of this wavelet basis 2 times, and then we put such a higher resolution wavelet basis function uniformly on the space like this. Then we iterated many times, infinitely many times. So this is our wavelet decompositions. Then we take the linear combination of these basis functions, then we can represent the target function f included in a Bessel space. Okay, so as I said, so the function f in a Bessel space has some sparse coefficient. That means that there are to represent the target function like this that employs these these basis functions, wavelet basis function, and around here, so the target function has a higher frequencies. So then it may employ this higher resolution basis functions. But maybe around here, the target function is very smooth. So it doesn't need such a higher frequency. So then the coefficient around here could be almost negligible. Okay, so the coefficient for this basis function is very small. The coefficient for this basis could be large. So then you can see some sparsity of the coefficients in all of these expansions. Okay, so then you can see that the small p corresponds to the sparse coefficient. So actually, the p corresponds to the LP norm of the LP norm of the coefficient. Okay. So then, so by using this sparse representations, you can use some sparse estimation like a wavelet shrinkage estimators to obtain such a minimax optimal rate. So in that sense, a neural network is doing something like sparse estimation in a function class. But the difference from sparse estimation is that in the sparse estimations, you should prepare the wavelet basis functions beforehand. Okay. Okay. So I know that target function is in a Bessel space. So okay. So I prepare the wavelet basis function. Then we estimate the coefficient by using something like sparse estimations. So that is what we do in a sparse estimation. But in a deep learning settings, you don't need to know the target function is included in the Bessel space. Just fit the neural network to the data. So then the neural network can automatically find this kind of basis functions. So the internal layers tries to approximate this sparse the wavelet basis function to approximate the target functions. So that is a difference over the sparse estimation and the deep learning. In the sparse estimations, we choose the coefficient. We choose the basis function, but in a neural network, we construct the basis function in the internal layers. That is a difference. Okay. Yeah. So here is the proof strategy. So I just quickly explain the proof strategy. Okay. So as I said, the target function admits a wavelet decomposition like this. Okay. So for each target function FO, so we can select n important basis functions, n basis functions, and we discard other basis functions. And so there is a way of choosing the appropriate basis functions. So if you choose the appropriate basis, so we are choosing this important basis function, n basis function from the series of the wavelet basis. Okay. So then the approximation error can be bounded by n to the minus s over d. So there's a well-known result like this. The L2 error induced by discarding the other terms than the first n terms is bounded by n2 minus s over d. Okay, so now we know that the target function FO can be well approximated by this finite sum. So next, we try to approximate this basis function psi I by a neural network. Okay. So through the internal layers, the output from the last layer is psi hat 1 to psi hat n. So each psi hat I represents the approximation of the target basis function psi I. Then just taking their linear combination, then we get a good approximation of the target function. So therefore, if you use this neural network, then approximation error between the true target function f naught and our neural network model can be bounded by n2 minus s over d. So because we can very accurately approximate the weighted basis function psi like this. So yeah, so if the width is, the depth is L, we can show that such a weighted basis can be approximated by neural network of the order of exponential 2 minus L. So if the width is, the depth L is like log n, so L is like log n. So then the approximation error coming here is like polynomial to the n. So it can be very small. So therefore, this term can be neglected. So by paying the log n depth. So the main term is coming here. This is just n2 minus s over d. Oh, sorry, this 2 is not necessary. So 2 should be dropped. So yeah, anyway, so we have, so then by doing so we have approximation errors. So I mean, it's a model bias. Then now we put this model bias to the bias and the variance evaluations that I presented in the previous slide. Okay, the variance is a log governing number divided by sample size n, and the bias is the model bias just I presented here. Okay, here is the model bias. So it is like n2 minus s over d. So that is coming here. So the variance can. So variance is, sorry, the log governing number of the neural network is bounded by like this, by using the depth and width and the number of non-zero component, number of non-zero parameters of the neural network, then you get this variance. Okay, so if you set the depth is like log n, or width is order n, and S is so S is the number of non-zero components. So this is a little bit different from practical settings. So we consider a sparse neural network. So the number of non-zero component is like n log n, and so you don't need to consider here. So then the variance is like n over small n. So yeah, n divided by n up to the polylog orders. Okay. So n is basically the model size of the neural network, and small n is the sample size. And the bias is n2 minus 2s over d. So then what we should do is just balance this bias and variance. Then you get the optimal rate like this. This is what we have obtained in the previous slide. Okay, good. But so what happens for the linear estimators? Okay, so as for the linear estimators, there is a so-called convex Hull argument. So what is that? The minimax rate for the linear estimators is the same as the minimax rate of the linear estimators on the convex Hull of the target function class f. So what I said, okay? For any linear estimator S hat, f hat is some linear estimators like a kernel method. The worst case mean squared error is the same as the worst case error over the convex Hull of the function class f. Now, function class f is the Bessel space, unit model of the Bessel space. Okay, so if P is small, then that class can be non-convex like this. So that the function class is non-convex as a function class, okay, as a set of functions. That becomes like this. So if you take its convex Hull, the convex Hull becomes much larger than the original function class. Then the capacity, or so, I mean, the complexity of the model becomes large. Then there appears some discrepancy of the convergence rate of the components. Okay, so in some situations, we can extend this convex Hull to the Q Hull. So yeah, so instead of just a convex Hull, so we can take a kind of a minimum ellipsoid in L2 space. So then it can be much larger. So therefore, so linear estimators cannot distinguish a very small function class and the convex hull of that function class. So therefore, the linear estimator behaves as if the true function f is included in a much larger function class, the convex hull or the f. So then it suffers from the suboptimal range. So here's one example. Here's one example. Let us consider to estimate a piecewise constant function with 3 jumps. So okay, this is a very simple functions. So we know that there is a jump, there is there is a jumps at 3 points like this, and between the jumps it is a constant. We want to estimate this kind of function. You can see that this is not closed in a convex hull. So actually, if you take the convex combination of this function and this function, you have a function with 6 jumps. So just taking convex combination so that you can outside of the function class where so in which only the function with the 3 jumps is included. Okay. So therefore, by taking this convex hull, so the function class becomes very large. Then indeed, so we can show that if you use a neural network to estimate this very simple functions, you get 1/n rate of convergence as a mean squared error. But for the linear estimates, like Kerner method, it suffers from 1/square root of n rate of convergence rate. So there is a square root of n difference. There is a big gap. So yeah, so this can be explained by this convex hull argument. So yeah, by using this convex hull argument, so we can explain all the existing work, like the function, the true function is included in the piecewise smooth function class. So then I said the deep learning can be better than the Kerner method. And if the target function is in a low has some low dimensional structure, so the target of the deep can be better than Kerner method. So everything can be explained by this convex hull argument and some sparsity viewpoint. Okay. So yeah, the same thing is also happening in the sparse estimation and like boostings. So people usually use the XGBoost for tabular data. So it works very, very well. Why is it? So that one reason is that the XGBoost constructs a basis function in adaptive ways. Depending on the input X, it constructs some trees or some basis functions by using boosting. So it is a kind of adaptive estimation. So that makes a difference. Okay. So next, I briefly explain the cause of dimensionalities and how to avoid how the neural network can avoid the cause of dimensionality. But I don't go much into details of this topic, but I will go to the diffusion model. Okay. So the minimax rate in the Bessel space I presented in the previous slide is given by like this. So you can see that the dimension d is coming here in the exponent. So if the dimension d is very large, the rate of the convergence is very small. So this is called the cause of dimensionality. But however, the neural network works well in very high dimensional data, like image data. So MLSS data, this is not so high dimensional, but this is already 784 dimensionality. This is very high dimensional. So, but it is known that its intrinsic dimensionality is like 13 or 14. So it's very small. So maybe the neural network is make use of this small intrinsic dimensionality. Actually, from some theories, we can show that it is true. Okay, so this is called manifold regressions. So suppose that if the data is on a low dimensional manifold, whose dimensionality is capital D, the capital D is could be much smaller than the small d. So yeah, so this submanifold is very, very low dimensional. Then the rate of convergence could be like this. So instead of small d, capital D is coming. So instead of 700, 13 or 14 is coming into the rate of convergence. So this is good. So this is yeah, well, this is fine. Yeah. And moreover, we can a little bit to go beyond that. Okay, so but the data is not necessarily distributed on exactly on the low dimensional manifold. It can be a little bit outside of the low dimensional manifold. Maybe so there could be some noise. So then the data can be a little bit outside of the model. So, but its essential dimension is not changed. So because just noise is added. So how to deal with, how to consider this situation? Okay. In these situations, the target function only depends on these two directions. But the direction toward the orthogonal to the data manifold is non-informative. So this is just a noisy part. So yeah, target function, the output is not affected by these directions. So yeah, in that situations, the smoothness of this direction could be very large. I mean, the target function will not change so much toward this direction. So maybe target function is very, very smooth to this direction. But the target function is not so smooth. If the x changes from here to here, so maybe the target function becomes a little bit changed. So then toward this direction, it is not so smooth. Okay, so if you write down the smoothness to this direction as a S1, and then the smoothness to this direction is S2, and the smoothness to this direction is S3. So then S3 could be much larger than S1, S2. Okay, so that is that in these situations, the target function has a different smoothness depending on the directions. Okay, so in this case, the ratable convergence becomes like this. Okay, so remember that in our usual, the original Bessov class, the ratable convergence was given by like this, so n to the minus 2s over 2s plus d. But here, in this anisotrophic smooth settings, d doesn't appear. So instead of d, 1 is coming here, and instead of s, so s tilde is coming here. What is s tilde? So s tilde is a kind of a reciprocal sum of si. That is the inverse of the sum of si inverse. That is defined by like this. This is the inverse of the si inverse, the sum of si inverse. So in the D-dimensional space, and just S1 and S2 is small, and S3 to SD are very large. So only the two direction is informative, and another direction is non-informative. So then the S2 to, sorry, S3, S4, SD does not contribute to this sum because S3 is very large, so the S3 inverse is very small. So it doesn't contribute to these summations, then this can be neglected. Only the S1 inverse contributes, S1 inverse and S2 inverse contribute to this summation. So therefore, S tilde is free from the dimensionality. So it can be, so yeah, so then this ratable convergence is dimension free. So yeah, even though the input X is very high dimensional, then the ratable convergence is it's not affected by the dimensionality. So actually, we can construct this kind of a result for infinite dimensional input. So yeah, so this particularly explains why the deep learning works well in high dimensional settings. Okay, so now, I want to spend a little bit 10 minutes or 5 minutes, something like that, to explain the diffusion model. Maybe I will stop the middle of the diffusion model, and then I will take a coffee break after that. Okay. So far, I have considered just a regression problem. So it was a very easy problem. So input X, and we want to output some real value Y. That is a very easy problem. But nowadays, so we have many foundation models like a diffusion model and transformers. So they work very well. So why is it? So this kind of a very classic approach can also apply to this kind of recent foundation models. So I want to explain that here. Okay, so you are very familiar to diffusion models, I guess. So for example, so DALL-E model, so if you input this kind of a text, then it can generate this very natural image. So, and also there are many other models like stable diffusion and mid-journeys. And nowadays, it's very easy to generate this kind of images. And so maybe 3 weeks or 4 weeks ago, OpenAI announced Sora, so that can generate this kind of very beautiful movies. So it surprised all over the world. So in these models, they announced that they are using a diffusion transformer inside it. Okay. So yeah, so this is amazing. So, but we want to give some theory on this kind of foundation models. Okay. So now to do some theoretical analysis of the diffusion model, so I'm going to prepare some notations. So the notation I'm using here is a little bit different from the computer vision papers, but essentially they are the same. Okay. So the diffusion model consists of two processes. One is the forward process, and the second one is a reverse process. The forward process is the so-called OU process. Suppose that you are starting from the images, then applying the forward process, it converts to some Gaussian noise. Okay. And so the important point is that in the forward process, the initial distribution is the target distribution. I mean, so X0 is distributed from the true distributions, like the distribution with the natural images. We're starting from the target distribution that we want to generate an image from. Okay, we start from the target distribution, and then we run this forward process, and it really goes to some Gaussian process, Gaussian distribution. So once we change the target distribution to the Gaussian distribution, then we run the reverse process, which is described by this stochastic differential equations. Then you can go back from the Gaussian distribution to the target distributions. So this is a kind of trace back the process, forward process to the t equals 0. Okay. In the forward process, we run x0 to t equal t bar or something like that. We stop the forward process, and then the reverse process, we start from a t bar, and then go back to t equals 0. Then you get the distribution of x0, so which is the distribution of the images. Yeah, that is what we want to generate the data from. Okay, so I'm going to explain a little bit more details. Okay, as I said, the forward process can be written by this stochastic differential equation. This is called OU process. dxt is like minus xt dt plus the Brownian motion term. Maybe you are not so much familiar with stochastic differential equations. You can consider this discrete time dynamics. So eta is the step size. So xt plus eta is given by xt minus eta xt. So dt is eta. So okay, so dt is eta. So minus xt dt is minus eta times xt. And the square root of t dbt is translated to square root of 2 eta times gzi t. Gzi t is just a Gaussian noise, so standard Gaussian noise. So this is very easy. So you can see that this, if there is no Gaussian noise, there's no Gaussian noise, this differential equation converges to 0. Okay, so at each iteration, so xt tries to approach the origin 0. So yeah, so this xt exponentially converges to 0. So however, there is some noise. There is a Gaussian noise, so it does not converge to 0. Instead, it will converge to the Gaussian distribution. So it weakly converges to the Gaussian distributions. So here is more precise descriptions. Let pt be the distribution of xt. So pt is a marginal distribution of xt. So then the pt has explicit form like this. Okay. Now p0 is a distribution of the initial distribution x0. So this is an unknown, the true distribution. This is a distribution with an image. And for each initialization x0, so the conditional distribution xt conditioned by initial point x0 is given by this Gaussian distribution. So the mean is mu t x0 and the variance is sigma t squared. Mu t is exponentially converged to 0. So mu t is like exponential minus t. So that means that xt forgets the initial state exponentially. So but the variance does not converge to 0. So the variance will goes to 1. So because sigma t squared is like 1 minus exponential minus t. So as t goes to infinity, the variance goes to 1. So instead of the xt forgets the initial state, so it converts to the completely random Gaussian distribution. So its density function can be explicitly written by like this. Okay. So actually, so we can show that the KL divergence between the PT and the Gaussian standard Gaussian distribution converges to 0 in an exponential order, exponential minus 2t orders. So this is very fast. So if t is like log epsilon, so then the k, so after t equals log epsilon, the KL divergence becomes like epsilon. So yeah, so just running the forward process for y, so then the PT will sufficiently close to the Gaussian distribution. Yeah. So the good point is that so Gaussian distribution is very easy to handle. So it's super easy to sample generate a data from a standard Gaussian distribution. So then in the reverse process, we start from such a Gaussian distribution. Okay. Okay, suppose that you stopped time t bar. Then now we are going back to the t equals 0 from t bar. Okay, now we start from here. The Gaussian distribution is very easy to generate data. So we start from here. Then now we want to go back to the target distribution. You just need to follow this stochastic differential equations. Okay, so by using this stochastic differential equations, then the yt's distribution is the same as xt bar minus t. So here in the reverse process, in the reverse process, t equals 0 corresponds to t bar or the forward process. So the yt's distribution is the same as xt bar minus t. So if you run the reverse process to time t bar, then you can get the distribution of x0. Okay. So as I said, starting from the Gaussian distribution is very easy. So then just running the Gaussian, this is stochastic differential equations. Then finally, it can arrive at the original distributions. The good point of a diffusion process and a diffusion model is that even though the target function is very difficult to sample, so you can easily generate a sample from that. For example, so the target distribution is this multimodal distributions. Then just applying an MCMC is very difficult because there is a large valley between these two models. So jumping from this model to the second model is very difficult. Jumping over this valley is very difficult. So that is actually very open problem in MCMC literatures. But if you use the diffusion models, then you start from Gaussian distribution. So the Gaussian distribution is just a unimodal. It's very easy to generate the data. Then it gradually split into the two models. And finally, it can get a sample from each model. So this is why the diffusion model can generate a variety of images. Okay? It doesn't start from, it doesn't try to directly generate from the target distribution, but it starts from Gaussian distribution and it's generally changing the distribution to the target distribution. Then it is very easy to get that data. Okay, so here's one two examples. Okay, you start from the Gaussian distribution, then finally it converges to the distribution whose support is dinosaur. So this is not just depicting the dinosaur. The distribution has a support which looks like the dinosaurs. Okay, so each point corresponds to each image. Okay, so each particle is one image. So, yeah, so this is just two examples. It's interesting that the diffusion model can do that. Okay. Okay, so okay. So but the problem is that in reverse process, we don't know these score functions. So we should estimate this score function by some way, like a neural network. But practically, usually people use a UNet to estimate this score functions. Then in practice, we use this estimated score function instead. Then maybe sort of the distribution y0 is approximated by standard Gaussians. So we use this approximated process as a reverse process. Then, so how to estimate the score function is a problem. But there is a very nice theorem such that that is so-called Kirsanov theorem. So that shows that the KL divergence between the P0, that is a target distribution, and the distribution of our generated sample is bounded by the constant times the mean squared error of the true score function and the estimated score functions. So by applying just the Kirsanov theorem, you have an upper bound like this. So therefore, this means that you just needed to minimize this mean squared error to get a good quality of the good quality of the sample. If you can minimize this mean squared errors, so then the KL divergence between the true distribution and our generated sample could be 0. So yeah, that means that we are generating very natural images. So this is our target. So then the next question is how to minimize this score functions. But I want to defer it to the second part of this talk. So I'd like to stop here. So in the first half, I stopped here. As I said, so to make the distribution, generated distribution close to the targeted distribution, so we just needed to minimize the mean squared errors between the true score function and our estimated score function. Okay. So this is because the KL divergence between them can be bounded by these quantities through the Kirsanov theorem. Okay. But there's still some problem because inside of this mean squared errors, there is still the true score function. So this is unknown. Okay, so please remember that the true score. So the distribution PT is an integral of a Gaussian distribution with respect to the true distribution P0y. But this is unknown. So P0 is basically some distribution of the data. So this is unknown. So we should make use of another quantity to calculate some loss functions. Okay, for that, but fortunately, we can show that through very simple calculations, you can make use of the conditional distributions instead of the marginal distribution to calculate this mean squared errors. So yeah, through some very simple calculations, you can replace this one by a score of the conditional distribution of xt, conditioned by the initial distribution, initial state x0. So yeah, this is very good because this conditional distribution is just a Gaussian distribution. Okay, so remember that if you start from x0, then the OU process is just a Gaussian process. So you know the explicit form of the distribution. Like, okay, so sorry, I go back. You can see that this is the conditional distribution of xt, conditioned by the initial point x0. So this is just a Gaussian distribution. We have an explicit form of the density function. So it's easy to calculate. It's easy to calculate the score function of the conditional distribution. So actually, we have an explicit form of such a score function like this. So you can replace this by this. Okay. So, but another problem is that even though you can replace the score function by that of the conditional distribution, so you should take the expectation with respect to the initial point x0 and xt. Okay. So if you fix x0, so if you fix x0, so then the conditional distribution of xt is just a Gaussian distribution, as I said. So that this is just a Gaussian distribution. It's very easy to sample. But we don't know the distribution of x0. So we use data. Instead of taking the exact expectations, we take the empirical average over the observations. Suppose that you have a bunch of natural images, so then you just take the average over such a training data. Okay, so the expectation over x0 is replaced by this empirical average. And then after that, so just conditioned by the initial data point, xi. So xi is on each images. Then the sampling from xt is very easy, just run the OU process. Okay. Then so then we obtain a so-called empirical score matching loss which is basically computable. So it's very easy to optimize this by using a stochastic linear descent. Yeah. So just minimize this empirical score matching loss over the function class of a neural network, okay, where S is included in the neural network. Okay, so the S takes the input xt and t, and then output the d-dimensional vectors, which are approximated the nabla log pt. Okay. So so you can see that this is just a convex functional with respect to S. So the training is very stable. So now, our question is then, so how accurate our estimated process is. So yeah, so there are many theoretical analyses of diffusion models like this. So here, many approximation error analysis, and the most relevant analysis could be like this. So De Portoli is a very strong theoretician. He has contributed to this literature very well. And his work on the versus side distance between a generated distribution and the true distribution could be like order n to the minus 1 over d. So this is good, but unfortunately, so the same rateable convergence can be achieved by empirical distributions. Okay, so we have n data points. Then we measure the empirical distribution of n data points and the true distributions. So that Wasserstein distance can be like n to the minus 1 over d. So yeah, this rateable convergence does not say any benefit of using the score matching loss or something like that. And moreover, so many theoretical analyses assume that the score function can be estimated with precision of epsilon for any t. So for uniformly over the t, it is assumed that the score function can be well approximated or well estimated. That was an assumption, but we don't know. So this is true or not. So we should show this. So from the theories. Okay. So the question is, how accurate can we estimate the score functions from some statistical viewpoint? Okay. And moreover, so such an error. So how strongly such an error propagates to the final quality of the data? So that is the second question. And also, so the quality can be better than the n2 minus 1 over d or not. So actually, we can show that so if the distribution, the density of the distribution has some smoothness, we can go beyond this rateable convergence. Yeah. Okay, so this is the problem settings. This is a little bit similar to the non-parametric regression settings. Okay, so suppose that the true distribution has a density function p0, which is included in the Bessel space. So here again, there appears a Bessel space like this. So just you consider that the density function is S times differentiable. Yeah, that's okay. And there is some additional assumption, but this is just a technical assumption. I think this is not necessary. So actually, so these some very recent results show that this kind of assumption is not required. But anyway. And so then under these assumptions, what can we say? Okay, actually just under these assumptions, we can show that the neural network can estimate the score function very well, and eventually we have this bound. Okay, so this is a TV distance, total variation distance between the distribution of x0 and our generated sample y hat. So y hat is this is the sample we generate by using the estimated score function. Okay, so this is bounded by basically n2 minus s over 2s plus t up to polynomial orders. So log to the 9 is not so good. So this is huge, but so I think this is just an artifact of the proofs. I think this can be much improved. The instance is that the rateable convergence is n2 minus s over 2s plus t. So it is known that this is also minimax optimals. So in this presentation, there appears many minimax optimality many times. And not only the estimating the functions, but also estimating the probability density functions. There are well-known minimax optimal rate that says that this is a minimax optimal rate. So we cannot go beyond this rateable convergence. So therefore, the diffusion model can do the two things. One is sampling. Okay, so starting from a Gaussian distribution, so you can sample the data from the target distribution, which could be, the target distribution could be very complicated. It could be very hard to sample, but by starting a Gaussian distribution using the reverse process, we can easily sample the data from very complicated distribution. That is one thing that the diffusion model can do. The second one is that the diffusion model can estimate the distributions. Okay, so as I said, by using the score matchings, the diffusion model is intrinsically estimating the target distribution. So then, as the distribution estimators, it also satisfies the minimax optimality. So this result particularly explains why the diffusion model works so well in practice. Yeah, so this is almost a minimax optimal. So, okay, so I want to explain a little bit about the proof ideas. This is very much connected to the estimation with non-parametric regression settings, okay? So remember that, so in the process, so we should estimate a score function of a PT. So I mean, so number log PT should be estimated. So there appears as a kind of bias and variance trade-off to estimate this score function. So now, first, we evaluate the bias, okay? So number log PT is just a number of PT divided by PT. So this is a ratio between number of PT and PT. Okay, so in the proof, the proof strategy is to derive the approximation error of PT and number of PT individually. Okay, so if you can approximate a PT and a number of PT in an intermediate layer of a neural network, so then after that, neural network can calculate or can approximate the division operator. So number of PT divided by PT can be well approximated by the neural network. So it is a kind of a known result. So then we can approximate the final score functions. So then first, we should evaluate the approximation error of this each term. Okay. So for that purpose, we consider just PTX instead of number of PT. So we consider easy part. So as I said, so P0 is now included in the base of class. And as I have explained in a previous slide, the function in the base of class admits wavelet expansion like this. So that if you truncate the summation at the term n, so at the finite term n, then the approximation error could be like n to the minus s over d. Okay, this is a known result. And as for the PTs, PT was a kind of diffused density function. Okay, so that was given by like this. So it's so okay. So for the initial point is y. So that is generated from P0, and once y is conditioned, so x0 equal y is given. So then the distribution of xt is just a Gaussian distribution. So you can see that this is a kind of convolution of a P0 and so Gaussian kernels. So you can see that the PT is a kind of a Gaussian smoothed density function of P0. So yeah. So now, so remember, so we know that the P0 can be approximated by the finite sum of the B-spline basis functions, the wavelet basis functions. So P0y can be decomposed into like this. And for each basis functions, we apply the Gaussian kernel smoothing. So this is the expectation of the Gaussian expectation with respect to the xt conditioned by the x0. So then we have a kind of a diffused version of the B-spline wavelet basis function. Okay. So you diffuse the basis function, and you get a smooth basis function. So this we call this as a diffused B-spline. So okay, we call this is a diffused B-spline. Then you can see that the PTX can be represented by the finite sum of the diffused smoothed basis functions. Okay. So actually, so if T is sufficiently large, so then this is almost the Gaussian kernels. So then the PT is just a summation of the Gaussian kernels. So it's very easy to approximate. Yeah. So fortunately, we can say that such a diffused kernel, so the diffused B-spline basis function can be approximated by neural network very efficiently. So just with this log epsilon and depth log epsilon, The width is polylog epsilon, the depth is a polylog epsilon. Then you get epsilon accuracy approximation of the diffuse B-spline as a function of input x and t. So the two variable functions. As a x and t, as a function of x and t, we have an L infinity approximation errors. L infinity null approximation errors as epsilon. So this is very accurate. So then, therefore, so if we output phi hat I, so that approximates diffuse B-spline basis. So then just taking their linear combinations, then you can approximate PTX very accurately. So in the almost the same manner in the non-parametric regression settings, so with sufficiently large neural network, then the basis function can be well approximated, and the residual term could be like N2 minus S over D. So this is the basic strategy to derive the bias term. Okay, and moreover, through some calculations, we can show that nabla log PT can be approximated by neural network with width n and the depth is like polylog n. The approximation error could be n2 minus t, n to the minus s over d times some log n divided by sigma t square. Sigma t square is 1 minus exponential minus 2t. So yeah, you can see that there is a sigma t square. Sigma t square diverge as t goes to 0. So another t goes to 0, sigma t square is very, very small. So therefore, this approximation error can blows up. So as t approaches, so okay, so if t is large, so then the distribution is almost Gaussian. So then approximating its score function is very easy. So just a score function of the Gaussian distribution is a linear function. It's extremely easy to approximate. But around t equals 0, the score function is far away from the Gaussian distribution. So it is it can have a non-continuous part. So therefore, the approximation is easy. It is not easy. So there appears sigma t square here. So therefore, as I said in the previous existing work, consider that this approximation can be uniformly bounded by epsilon. But such assumption is very hard assumptions. So it's almost very difficult to achieve. But the reality is that, so approximating the score function around t equals 0 is difficult. So this part should be taken into account. Okay, so I skip here. So then anyway, so we have a bias and a variance trade-off. So in the previous slide, I have obtained this bias term. And the variance term is almost the same as the non-parametric regression settings. If the width, so the number of non-zero parameter is n times the polylog n, then the variance is n times polylog n divided by sample size n. Okay, so there's a bias and a variance trade-off, but it's easy to balance these two terms. But here, so as I said, here is a sigma t square, so that can diverge as t goes to infinity. But so we don't need to take t equals 0. So we just stop just before t equals 0. Yeah, so we can use such a sample, so not t equals 0, but t equals t bar as a final result. So but there can appear some additional errors like this, but it's not so large. Yeah. So by taking carefully the truncation time, like t, the underbars, then sigma t square is still bounded, and also and also so we have a good bias and variance trade-off. Okay. So yeah, so by balancing the first term and the second term, so we have this one. Then so you have the minimal optimization. So that is a very good strategy. So the basic idea is very similar to the non-parametric regressions, but so we should take care of some specific issues corresponding to the score matching and the diffusion models. But it can be resolved like this, because even though sigma t square diverges, you can truncate the t equals t small underbar, and also by taking the integral, so then this term is not so problematic. Then we get this the usual bias and variance trade-off. Okay, so this is our proof strategy, and moreover, the images is very high dimensional, but the diffusion model works. Yeah, and also the diffusion model can generate movies. So movie is also very high dimensional. So why it works? So to explain it is very difficult, but here's one particular explanation. So suppose that there is a d-dimensional space, but the data, again, so we assume the data is distributed on a low-dimensional subspace. We assume that so its dimensionality is d prime. So d prime could be much smaller than d. So we assume that so there is some intrinsic dimensionality of the data. So actually, so if you randomly generate a Gaussian random variables, so okay, so then you can rarely find natural images. So that means that natural image distributed on a very specific manifold. So to hit such a manifold by a random Gaussian is very hard. So yeah, therefore, so that means that, so the natural image lies in a very low dimensional manifold. So the d prime could be very small. So in that case, so under this situation, so we can also show that the diffusion model can approximately identify the support of the distributions, then the rate of convergence can be improved. So in the previous slide, the rate of convergence in the X model, there was a D. But if the distribution has a low dimensional structure, so D is replaced by D prime. So this means that, yeah, neural network can find a low dimensional submanifold. Then you get the better rate of convergence. But I should remark that, so instead of a TB distance, we are using the Wasserstein distance. This is because if the data doesn't have a density functions, so then it is very hard to measure the TB distance. So TB distance doesn't make sense. So we should change the metric. So here we employ the Wasserstein distance. So this is also known as a minimax optimal in terms of the Wasserstein distance. So yeah. So therefore, so this theorem particularly shows that the neural network or so diffusion model can identify the low-dimensional structure, and also it is very adaptive to such a structure, and in a sense that it can achieve this minimax optimal rate. Okay. So I skip this one. So finally, I want to mention something on our work on the transformers, but I don't go too much into details. So this kind of non-parametric regression analysis can be also applied to transformers. Yeah, and roughly speaking, transformer can do a kind of feature selections dynamically. So what is a dynamically? So for each input sequence X, maybe the text, so the transformers get some text as an input. Therefore, each input X, it can select important features, I mean, so important tokens. It finds the important tokens, and then depending on input, such a important tokens, it makes the output. So this is a kind of a feature selections. So even though the text is very long, but inside the text, it finds important information from that, and it extracts the important information, and then so it can avoid the recursive dimensionality. So yeah, we can show the transformer can do that, something like this. But I don't go much into the details. Okay. So now I'm going to the optimization section. But I should make one remark on the rate of convergence. So in the first half, I have talked about only the rate of convergence. And then I have compared the rate of convergence between a neural network and a kernel method. And I said deep is better. But this is only about the rate of convergence. The actual performance could be different. Okay, even though the rate of convergence is fast, so behind the rate of convergence, there could be huge constant. That constant could be large. So therefore, so for small sample size, it is very much likely that the shallow method can outperform a deep learning. But as the sample size n goes to infinity, so then the scaling law of deep learning is better than shallow method. So what I'm saying is just a scaling law. I'm not talking about the hidden constant. So yeah, so we cannot say deep learning is always better than the sharp method. So it's better or not depends on the number of data points. Okay. Okay, so now I'm going to the optimizations. Okay, so far, I have talked only about the statistical properties, but I want to discuss the optimizations. So I neglected any problem about optimization in the previous slides, but it's very difficult issues. So to say honestly, in the literature, so there is not very strong result on the optimizations. So people are just working on a two-layer neural network. So it's very hard to show the global optimality of the stochastic gradient descent for the deep neural network. But I want to explain some progress of this literature here. Okay, so now, so you know that the deep to obtain a deep neural to perform the deep learnings, we need to optimize some loss functions. Okay? So maybe the number of parameters could be very large, like millions or billions. So we should perform the optimization of the very high dimensional problem settings. Okay. But the problem is that the loss landscape could be highly non-convex. So if you visualize the loss landscape, then it looks like this. Yeah. So there could be some local optimal solution. So if you do just a gradient descent, maybe it is captured in local optimal solution. So it is very difficult to find a global optimal solution. However, the stochastic gradient descent works well in practice. Why is it? So why is it? So that's a question here. One interesting result here is it's a kind of classical result that if you are considering a linear neural network, that means that there is no nonlinear activation function. Then the linear neural network is not degenerated. I mean, at the initialization, it doesn't degenerate to the low rank solution. So then linear neural network has no local optimal solutions. I mean, in other words, every local optimal is global optimal. Okay, so yeah, so this is good. So this is very much related to the matrix completions. So in 2016 or something like that, so people showed that the low rank matrix completion has no spurious local. So if you find some local optimal solution, so then it is already the global optimal solution. So, but this is restricted to the linear linear network. So what happens for the deep no linear network? So here's one encouraging result. So let us consider just a two-layer neural network. So yeah, so we restrict ourselves to the two-layer neural network, and we have n data points. And the loss function is convex, like a squared loss or logistic loss. But even though the loss function is convex, maybe the loss with respect to the parameter itself could be non-convex. So this loss function is convex in terms of the function value of the neural network. It's convex. So we assume that. Then now we want to fit a two-layer neural network to the data. So that if the width of the neural network is larger than the sample size, and also the activation function is continuous, then there is no spurious local minimum. And I mean, so every level set is connected. Every level set is connected to the global optimal solutions. The level set is that you cut the function at this level, and then you consider this lower set. Yeah, so then this is connected. This is connected. So in other words, for each point x, there must be some path from point x to the global optimal solutions. So on this path, so you don't need to increase the loss. So yeah, so you can. Yeah, so you can find a path. So along which you don't need to increase the loss values. So therefore, maybe so from this theorem, it is so we expect that the stochastic gradient descent or the gradient descent will go around the global optimal solution. But unfortunately, this theorem doesn't say that. Because even though there is a path, the path could be very long plateaus. So then the gradient descent can capture the plateau. So maybe, so there's no guarantee that SGD or gradient descent can merge to the global optimal solution. Anyway, so we want to show the convergence of the gradient descent. So, so from this theorem, so we can expect that wider network is better in terms of the optimization. Actually, it is true. So by considering the very over-parameterized networks, so there is no spurious local optimal solution. So then by using these notions, there are several analyses. So the typical analysis is a neural tangent kernel analysis. The second one is a mean field analysis. Yeah, so neural tangent kernel appeared in the question in the first half, but yeah, so there are two regimes. The difference between neural tangent kernel and the mean field regime is the scaling of the initializations. Okay, so just for simplicity, let us consider two-layer network. The first layer's parameter is WJ, and the second layer's parameter is AJ. Okay, so we consider very wide neural network. If the second layer's parameter has 1 over square root of m scaling, then this is called a neural tangent kernel, where so m is the width of the network. And if AJ is like 1 over m, then this is a mean field regime. So if you take the 1 over m, so this is just an average of each neuron's output. Yeah. So then in that sense, the neural tangent kernel has a larger scaling. So this is a square root of m times larger than just taking an average. So in that case, in a neural tangent kernel regime, so because the scaling is like a square root of m times larger than just an average, so small change of the first layer has a great impact to the output. Okay, so compared with neural tangent kernel and mean field regimes, so square root of m times larger impact on the target the output. So therefore, just changing the first layers a little bit, so then you can have a good change of the output. So in that sense, you can consider a kind of first order approximation of this part. So even though there is a nonlinear activations, just taking a Taylor expansions, the first order variations, then so first order Taylor expansion can explain the behavior of the neural networks. That is a neural tangent kernel regime. But in a mean field regime, so we take it 1 over m. So therefore, the small change of WJ will not affect the output. So you should change the first layer WJ very much so that output is changed. Okay. So then that means that the first layer should move very far away, which corresponds to the feature line. Okay, so let's see the difference in these figures. Okay, let us consider just a regression problem where the true function is represented by the two neural network. Okay, the true function is determined by like this. So that this is a teacher-student setting. So teacher has only two neurons. So we just try the student network to this data. So if you use the neural tangent kernel regimes, then the solution path can behave like this. Okay? So we fix the second layer's parameter. So we only train the first layer's parameter. Okay? So the input x is a two-dimensional. So the first layer's parameter is also two-dimensional. And so each line corresponds to the trajectory of during the optimization of each neurons. Okay. Okay. So each path. Okay. So each line corresponds to each neurons. So yeah. So the blue dot is the initialization, and the yellow color is the trajectory. So you can see that for neural tangent kernel regimes, each neuron, each parameter doesn't change so much. That is almost around the initializations. Okay. However, for the mean field regimes, so you can see that the WJ, so the first layer's parameter travels a lot. It moves a lot. From here is an initialization. It moves from here to here. And interestingly, it converges to the one of the directions of the two neurons. So you have two neurons. And so that means that you have two directions as two directions. So each neuron converges to one of them. So one of the two neurons. So yeah, so this is the future lines. Okay, in a neural tangent kernels, the training dynamics doesn't show any feature learnings, but in the mean field regimes, you can see feature learning. So and moreover, interestingly, so because all neurons aligns to the two neurons directions. So then the intrinsic dimensionality, I mean, the degrees of freedom of the trained network is much small. So because because almost all neurons are in the same directions. Almost all neurons are identified. So even though in initializations the neurons are directed, so the WJ is directed to many directions. But after the training, it converges to just two directions. The intrinsic dimensionality is just two. So that means that the complexity of the model is also reduced so much. Now, that's a very interesting phenomenon. So this could be related to a kind of intrinsic regularization, implicit regularization. Okay. And so as I presented, so there were two regimes, like neural tangent kernel and mean field regimes. And more generally, there are many other parameterization, or many other regimes. So actually, so beyond the between an NTK and mean field, so there are many scaling, the choice of the scalings. Okay, so here is a way over unifying way over. So dealing with such a scaling in a unifying manner, so that is called ABC parameterizations. So Grekian proposed these parameterizations. So we have three parts of the parameterization. The one is so the parameter WL is parameterized by n to the minus AL times small WL. Small WL is the actual training parameter. We train this parameter, but what we use in neural network is large WL. So we change some scaling. And as for the initializations, so small WL is initialized in mean 0 and variance n to the minus 2b. Oh, sorry, n is the width. So sorry, I should say that n is the width of the network. Okay. And the learning rate is set to be the eta to the n to the minus c. So by changing the a and b and c, so you can construct many different configurations of scaling. Okay. So in a mean field regime is given by like this. So AL is 0 for the L equal 1, AL equal 1 for L equal 2, something like that. So yeah, so mean field regime on a neural tangent kernel regime can be two specific examples of this ABC parameterizations. And so the Grekian proposed a mu-p parameterization. So this is to make the variance of the internal features to be 1. And also under this scaling, so we can perform the feature runnings. So not just a neural tangent kernel, so it can perform this feature running. So that is their proposal. So mu-p parameterization. So what is the benefit of mu-p parameterization? So the good point is that the hyperparameter can be transferred from small model to the large models. So okay, so as I said, so there's a scaling parameters depending on the n. N is the width. So that means that if you change the width, then the scale or the magnitude of each parameter could be changed. But how to scale compared how to scale the magnitude parameter relative to the width n. So that is our questions. But if you follow the mu-p parameterization, so you see this kind of invariance. Okay. And each line corresponds to each width of the network, and the horizontal axis is a learning rate. So you change the learning rate, and the vertical axis is training loss. But the training loss is almost the same as test loss. So you can see this is just a test loss. Of course, so usually you see this kind of curves. By changing the learning rate, the optimal learning rate could be different depending on the model size. So depending on model size, the optimal model, learning rate could be different. But if you employ the mu-p parameterizations, the optimal learning rate is the same across all the model size. So this is a very nice properties. For example, so please consider that you want to train the GPT-3 or GPT 3.5 or maybe GPT-4. So it could be a huge model. So you don't want to do the hyperparameter search. So Then in that situations, by using this mu-p, you start from a small network, and then you find the optimal hyperparameters. Then following this mu-p parameterization, you just scale the hyperparameter, so like learning rate, initializations, and parameterizations. Then you get also the optimal the learning rate, or so optimal hyperparameters, even for the larger network. So then you can save the money. Okay? So you don't want to do the hyperparameter search for the very large network. Just a training one model is like billions dollars. So then we don't want to waste that time, waste the money. So yeah, then in that sense, this is useful. But sometimes this could be very unstable. So sometimes it works very well. Okay. And moreover, so if you talk about optimization of neural networks, there appears a so-called implicit regularization. Okay, so let us consider the two-layer neural network like this. So this is written by the integral representations. So eta w transpose x, eta is a ReLU, eta w transpose x is one neuron. We take the integral with respect to some signed measure rho. Rho is a signed measure. We optimize this signed measure rho by minimizing this some loss function. Now we are considering just a binary classification task. And so Tizat and Bach, so in this paper, they show that if it converges to some global optimal solutions, so then the converged solution should be the max margin solution under L1 normal constraint. So that means that, so this is the more precise definition here. So you mean that, so they try to maximize the margins. So with L1 normal constraint, so then the solution becomes sparse. Sparse means that so many neurons can be discarded. If some neurons is not useful, so that is neglected. Just the useful neurons survive. And for example, so if the data is aligned in just one direction, then the neuron aligned to that direction only survives. Okay. So this is a implicit regularization of a neural network. So, but if you use something like the Kernel method, then this L1 norm is replaced by L2 norm. So you don't have our sparse solutions. Of course, it depends on the true target functions. But if the target, the true optimal boundary is very, very simple, then the sparse solution could be better. Okay, so here's some intuition of the implicit regularization. You start from some initialization here, then depending on the optimization technique, it converges to somewhere of the set of solutions. So this point, the conversion point could depend on the optimization techniques. So, and also it depends on the models. Okay? Maybe it converges to somewhere else. But for the neural network, maybe so it converges to the minimum L1 normal solution in the all set of the optimal solutions. So this is called the implicit regularization. Okay. So this is a more algorithm-induced implicit regularization. So if you change the optimization techniques, so then such an implicit regularization could be changed. Okay, so actually, so if you use the NTK regime and they use so just a stochastic gradient descent, then the appeared implicit regularization is a L2 regularization. But in a mean field regime, so as I presented, so L1 regularization appears. So yeah, so if you want to have sparse solutions, then the mean field regime is better. So this is consistent to what I said in the first half of this lectures. So in the Bessel space, the neural network corresponds to the sparse solution, sparse estimations. So in terms of optimizations, the mean field regime can do similar thing. So yeah, there's a connection between this observation and statistical optimalities. And also, this kind of implicit regularization is connected to something like glocking and binomial overfittings. This figure is coming from some recent works. So I only just say some intuitive explanations. Okay, in the glockings, first the training error drops rapidly. After that, the test error drops. So after that training, after we proceeded training several times, then the test loss, so test accuracy goes up. Okay, first the training loss, training accuracy goes up, and after that, test error follows. So here is a so-called hidden progress. So why is it? So this is a bit kind of easy to understand intuitively. So now we are considering just the binary classifications. So to perform the binary classification, the classifier can have a very small values. So okay, we start from very small values and then take the one gradient descent. So then the value is updated. And so if the model is sufficiently large, like it is sufficiently high dimensional, then just the first one gradient descent, you can separate the data completely. That means that training error can be zero. So that 0-1 loss, so in terms of 0-1 loss, that training error can be zero. But of course, the loss is not converged to zero. So like a logistic loss is not converging to zero. But if you look at just a 0-1 loss, the very fast gradient descent can memorize the data, so then the error could be zero. So after that, after the network memorizes the data, but the loss is not converged to zero. So the model tries to minimize the loss goes to zero. Then the implicit regularization works. Then the solution tries to find a minimum L1 norm solutions. That means that the margin is, so they try to maximize the margins. Then the test error goes up after that. So this is the mechanism of blocking. So in recent months, so in the last few some papers that show this kind of a phenomena in the high dimensional settings, and they show the binary overfitting and blockings. Okay, so this is one of the hot topic now. Okay, so now I'm going to a little bit more kind of a solid mathematical things, the noisy gradient descent. Okay, noisy gradient descent. So as I said, so the loss landscape is non-convex. So if you use a vanilla gradient descent, maybe the solution is captured in the local optimal solution. But the SGD works well in practice. The one reason is that the SGD has a randomness. So thanks to the randomness of the SGD, it can escape from the local optimal, and eventually it converges to the flat global optimal solution. That is what people believe. So then we see some such a experimental result, and there are many theoretical justifications on that. Okay, so here is also another figures that explains the effectiveness of the randomness. Okay, so thanks to the randomness of the stochastic gradient descent, so it can easily out of the sharp local minimum, and it's likely to stay the flat minimum. And then the people believe that the flat minimum is good for generalization. Then so that we have a good generalization of neural network. Yeah. And also another paper, this paper showed that, so this stochasticity of SGD works as a smoothing of the objective functions. So actually, so the SGD can be treated like this, nabla objective plus some noise. So by taking the expectation with this noise in the second step, so in the next step, so then this can be seen as a stochastic gradient descent of the smooth objective functions. So because of this noise, so you can consider a kind of a convolution or Gaussian noise and objective function. So then you can smoothing out this fluctuations. Then you get a smooth objective function like this. So then, thanks to this smoothing effect, the SGD is not captured by the local optimal solution, sharp local optimal solution, but it converts to the flat global optimal solution. So yeah, so this kind of analysis particularly explains why SGD works well in practice. Okay. Now, so I want to explain a little bit relevant theories of Langevin dynamics. Okay. So as we have seen, the stochasticity of SGD is very important to obtain a good solution. So Then to deal with such a stochasticity in a more mathematically rigorous way, we consider this stochastic differential equation. This is called Grant-Langevin dynamics. Okay, so now L is the loss function, which could be non-convex. So we want to optimize this non-convex objective function. This is a very difficult problem. So we basically do the gradient descent. So this is basically this is a gradient flow to optimize the loss function L. But we add a Brownian motion term like this. Here, lambda controls the strength of the Brownian motion term. Okay. So under some assumptions, it is known that xt has a stationary distribution pi, which is given by exponential of minus L over lambda. So if lambda is small, and then so the stationary distribution pi concentrates around the global optimal solution of L. So actually you can see that if Lx is very small, then pi x is large. So that means that the stationary distribution has a high probability mass around the global optimal solution. And however, if L is flat around the global optimal solutions, so then the pi has a larger mass around the global optimal solution. So then this explains why the noisy gradient descent, like this is Grant-Langevin dynamics, likely to stay the flat global optimal solutions. Okay. So, but this is a continuous time dynamics, so maybe it's easier for you to understand the discrete time dynamics. The discrete time dynamics is given like this. Okay, so eta is the step size. So the Grant-Langevin dynamics. So you first perform the gradient descent, then you add some Gaussian noise, like this, Gaussian noise. So now, I would like to consider the convergence property of the Grant-Langevin dynamics here. But I should say that GLD is a little bit dependent by SGD. So yeah, in the SGD, the noise is not Gaussian, and also it could be more heavy-tailed, and also the variance of the noise is not isotropic; it could be anisotropic. So this is a little bit too much idealized. But just for rigorous mathematical derivations, we consider this one. Okay. So the interesting characterization of a Grant-Langevin dynamics is that it is a Wasserstein gradient flow to minimize some functional L like this. Okay. So what is that? So it is well known that in the literature of probability theories, there's a Fokker-Planck equations. The Fokker-Planck equation describes the evolution of the distribution of xt. So here mu t is the distribution of xt. So then we want to trace the dynamics of mu t. So it is known that for this stochastic differential equations, the mu t follows this partial differential equation. So this is called the Fokker-Planck equation. dt mu t is given by nabla dot something. Yeah, this is a Fokker-Planck equation. And so we can show that this is trying to minimize this objective function. Actually, more precisely, this is a Wasserstein gradient flow to minimize this objective. So you can see here is a nabla L, and here is nabla log mu t. So nabla L corresponds to minimizing the expectation of L with respect to the distribution mu. And the nabla log pt corresponds to entropy. So entropy is defined by the expectation of log mu. So this could be like a negative entropy in a terminology of information theories. But in mathematics of property theories, people usually say this is entropy. This is not a negative entropy, but this is entropy. And this is a convex function with respect to mu. Okay. So okay. So then so that means that the Grant-Langevin dynamics is trying to minimize this functional. The first term is linear functional. It is just an expectation of L. The second term is like a strictly convex objective. That is entropy regularizations. Okay. So this is denoted by L mu. Okay. So you can easily check that the minimum of this functional is the stationary distribution. just taking a variations, just take a first order variations, like yeah, so variational method, so that you can easily check that a minimum of this objective is mu star, which is given by exponential of minus Lx divided by lambda. So in other words, the gradient differential dynamics is solving convex optimization in a measure space. Okay, so if you look at xt, so Lx could be non-convex, but if you look at the probability measure of xt, so then what the dynamics is doing is just a convex optimization in a measure space. Okay. So I should mention about the continuity equations. So maybe this could be a little bit very details, much details, but okay. So anyway, so the Fokker-Planck equation was given by like this. So this is a dt mu t is given by nabla dot mu t times something, some vector field is coming here. Okay, this is a so-called continuity equations. If the dt mu t is given by minus nabla dot bt and mu t, so this is called continuity equations. So in the Fokker-Planck equation of gradient differential dynamics, the bt was given by nabla minus nabla Lx plus lambda times nabla log mu t. Yeah. So yeah, so the GLD corresponds to one of the specific quantity equation. The precise meaning of this formulations. So this description is like this. This is a more rigorous definition of quantity equations. Okay, so suppose that you have some test function f, or any test function f, if the time derivative of expectation of fx is same as the nabla fx, the expectation of nabla fx transpose bt, like this. So then we say that mu t follows this quantity equations. So this can be understood by considering just integration by parts. Okay, so taking the derivative of mu t with respect to t, so then you have a minus nabla dot bt mu t, so like this. Okay, then taking the integration by parts, nabla can be coming here, then you get the right hand side. Okay, so so yeah, so if you consider the integration by parts, so this definition is very natural. So following these definitions, so you can understand the more precise definition of the quantity equations. Okay. For that purpose, let TT be a map generated by a vector field Bt. So and that means that so we start from X and we follow the vector field Bt, and then so the particle starting from X will move to TTX at time t. In other words, so the time derivative of TTX is Bt over TTX. So sorry, it is a bit complicated. So okay, so at time t, the x is moved to the location TTX. So and now that particle is further moved to the direction of the Bt. Okay, so this is like a velocity of each particle. So by using this map, so we can see that mu t is a push forward over mu zero by this map tt. I mean, so mu t is a push forward of mu zero through the map tt. So in other words, mu t is a distribution of ttx where x follows the initial distribution mu zero. Okay, x is generated from mu zero, and now x is transported to ttx. And what is the distribution of ttx? That is the mu t. So we can show that. So now I would like to check this statement. So then, yeah, so just we need to check this quantity equations. Okay. Now, so we take the derivative of the expectation of fx with respect to t. So as I said, mu tx is a push forward of mu zero by the map tt. So then this expectation can be rewritten by like this. So this is the expectation of ttx with respect to the mu zero x. Okay. So but now just we want to take the derivative of ftTx. So we admit the exchange of our integral derivative. And so just a chain rule. So the derivative of this term becomes nabla f ttx times dt over tt. So this is just a chain rule. Okay. Then now, so because TTX follows the vector field BT, so this time derivative is like a BT TT, like this. So you can see that here is a TTX and a TTX that is taken expectation with respect to mu 0x. Then because TTX follows the mu t, so this expectation is the same as this. Instead of the mu 0, so you can use a mu tx as a measure because the distribution of a TTX is mu tx. Okay, so you can notice that. So under these characterizations, you can see that mu t satisfies the quantity equations. So yeah, so there's some connection between BT and some particle movement. So this is the precise meaning of the quantity equations. Okay, so this kind of notion will appear in the latter half. Okay, so I skip here. So by using this kind of observations, now so we want to take the derivative of objective function L. So yeah, so I said that the grand differential dynamics is trying to minimize L mu. So L mu was given by the expectation of L plus lambda times the entropy. Yeah, so that we take lambda inverse for both sides. Then we have this one. So then we know that mu star, the optimal solution is an exponential of minus Lx divided by lambda. So Lx divided lambda is coming here. This is just a log of mu star. This is a minus log of mu star. So this term is minus log of mu star. This term is minus log of mu star, plus some constant. And by definition, the entropy is expectation of log mu. Okay, so by combining these two terms and we neglect the constant, you can see that there is an expectation of log of mu over mu star. Okay, so here's the log of mu over mu star. So you are I think you are very familiar with this formulation. This is just a KL divergence between mu and mu star. So in other words, so I said grand differential dynamics is trying to minimize the function of L mu, but L mu was just a KL divergence between mu and the optimal solution mu star. So yeah, in other words, so the GLD is trying to minimize the KL between the mu and the optimal solution mu star. So now we take the time derivative of KL mu t. Okay, so we want to see so this KL divergence actually decrease to 0 or not. We just take the derivative and then so we put this derivative into the integral. So first, we take the integral of, we take the derivative of this mu t like this. And next, we take the derivative of log mu t here. So the derivative of log mu t is dt mu t over mu t. So this denominator mu t is canceled out with this term. So this is just the integral of dt of mu t. But so the expectation of mu t is always 1. So it doesn't depend on t. So this term should be 0. So okay, so you put this derivative outside of integral. So this is a dt of integral of mu t dx. So the integral of mu t is just 1. So its time derivative should be 0. And also, so here is the derivative of mu t with respect to the time t. So by the definition of the continuity equations, so this should be nabla dot minus bt t, and this means that like this, okay. And so nabla of log mu, so bt, so the inner product between mu t and the nabla of log mu t divided by mu star is coming here. So this is the time derivative. Okay, so what we have obtained is like this. So the time derivative of the KL divergence is given by like this. So now also remember that, so if for a grand differential dynamics, BT was just like this. BT was minus lambda nabla log mu t plus nabla L. So we know that lambda L is just lambda of nabla log mu star, because mu star is exponential or minus L divided by lambda. So yeah, nabla L can be constant times nabla log mu star. So you can see that this term and this term is the same. This term and this term are the same. So actually, so if you substitute this Vt to this formulations, you can see that the time derivative of KL divergence is the same as minus lambda of Fisher divergence. Okay, so what is the Fisher dynamics? Fisher dynamics is defined by these two formulations. So nabla log mu, so the Fisher dynamics between mu and nu is the L2 distance between the nabla log mu and the score of nu and mu. So this is another divergence than the cave divergence. So through this analysis, the GLD tries to minimize the cave divergence. And moreover, the time derivative of cave divergence is the same as minus lambda of the Fisher divergence between current solution mu t and the global optimal solution mu star. So as long as the Fisher divergence between the mu t and mu star is not zero, then the cave divergence continues to decrease. So it will stop until it will not stop until the mu t will converge to the mu star in terms of the Fisher divergence. So then it is expected that the mu t will converge to the global optimal solution star. Okay. So then the next question is how fast the rate of convergence is. So to derive the rate of convergence, the one with a very, very typical equivalent is a log sovereign inequality. So people usually assume that the mu star, the target distribution, satisfies the so-called log sovereign inequality. So what is the log sovereign inequality? So if the mu star satisfies this inequality for any nu is any probability measures, the K divergence between nu and mu star is bounded by some constant times the Fisher divergence, then we say that the mu star satisfies the log sovereign inequality. I will show some sufficient condition for this log sovereign inequality. But anyways, under these conditions, so we know that the derivative of KL with respect to the time t is the same as minus lambda times the Fisher divergence. So under this log sovereign inequality, this right-hand side can be further upper bounded by minus 2 alpha times the KL divergence. So once you arrive at these formulations, this inequality, then just applying the Grombol's inequalities, you have an exponential component. Okay, so dtKL is bounded by minus constant times KL. So you have an exponential components. So you have a linear components with the KL divergence. So yeah, so then everything is reduced to show the log sovereign inequality of the optimal solution mu star. So there are many ways to guarantee the log sovereign inequality, but I just only show the two situations. One is the strongly convex settings. If the L, sorry, this is too small, but if the L, the objective function L is strongly convex, then the mu star satisfies the log sovereign inequalities with constant alpha, which is more bounded by mu or L, mu over lambda. So mu is a strong convexity of the objective L. So like, for example, if the Gaussian distribution, let us consider Gaussian distributions. The Gaussian distributions, the standard normal Gaussian distribution satisfies the log sovereign inequality. So another example is the Hori-Stork bounded perturbation lemma. So this is also a very famous result. Suppose that the mu star, this is a stationary distribution, is given by the product of mu x times some finite variation, exponential of hx, where h is any bounded function. And we also assume that mu x satisfies some log sovereign inequality with constant alpha prime. So then the mu star also satisfies log sovereign inequality with a constant alpha, which is given by like this. So, okay, so suppose that you have a Gaussian distribution, then the mu star is some finite perturbation of such a Gaussian distribution. So then it also satisfies log sovereign inequality. Yeah. So, okay, so there are some related work here. And now, so I want to apply this general theory to show the convergence of a two-layer neural network. So, okay, so here, so let us consider just a mean field neural network. Okay, so because in the neural tangent kernel regime, so the optimization is easy. So let us consider more difficult settings. Okay, so this is what we consider here. So each neuron is given by the first layer is a parameter Wj and a nonlinear activation, and the second layer is parameter Rj. And we denote by hx each neurons, where so x is each neuron's parameters. we take their average like this. Okay. So now we try to fit this two-layer neural network to the data by minimizing the loss functions. The loss is assumed to be convex, like a squared loss and logistic loss. We also add some L2 regularization like this. Yeah. So, but this is still non-convex. So then we try to apply the gradient Rajman dynamics. So if the objective function satisfies log sublimation equality, we have the exponential component. So we apply the gradient Rajman dynamics like this. But unfortunately, very naive application of existing result shows that we need exponentially many iterations, like exponential to md times log 1 over epsilon, where d is the dimensionality of the input and m is the width of the network. So this is very bad. So yes, so just naively calculating or evaluating the log sublimation constant. So then there appears like exponential to m. So m is the width of the network. So if the width is very, very large, then this is not so good. So like if the width is like 1,000 or something like that, there appears an exponential to 1,000. So this is not so good. So then that means that noisy gradient descent, so maybe you consider that noisy gradient descent is not a good way to show the convergence of the neural network, but the reality is not true. So actually, so we can generalize it to a more general like a mean field Rangman dynamics. Then we can show the convergence without exponential dependency on the width. So that can be realized by taking a mean field limit. Okay. So far we have considered a finite width network. It's a finite width. The width is just m. But we take m to infinity. So okay, so instead of m to be small, but we take the m to infinity, then this average could converge to these expectations. So here, mu is a distribution of the parameters of neural network. Mu is a distribution of our neural network parameter, each neuron's parameter. So, okay, so if you look at each parameter, R or W, then the network is nonlinear with each of the parameter. But if you look at this integral representation, this is linear with respect to the distribution of mu. So you have a infinite dimensional linear model here. So yeah, this is a good point. So we have an infinite dimensional linear model. So then maybe it sounds like we can converge to some global optimal solution. Yeah. So by taking this mean field limit, we can replace fx by f mu, and so regularization term can be replaced by the expectation like this. So this is a new objective function. We want to optimize this objective function with respect to mu. So since f mu is linear to the distribution mu, so this is a convex function, and this is also linear function, so this is also convex. Yeah. So how to solve this? And then there is so-called mean field Rangman dynamics. This is a direct extension of a usual Rangman dynamics. So in the mean field Rangman dynamics, we try to minimize this convex objective functions. So f mu is a convex functional. The definition of the convex functional is like this. The convex in terms of the linear space. So f of theta mu plus 1 minus theta nu is bounded by theta fc f mu plus 1 minus theta f nu or something like that. This is a convex functional. And we also add an entropy regularization as in the gradient Rangman dynamics. So then to optimize this objective function, the mean field Rangman is defined by like this. So yeah, we follow, so in the mean field Rangman, so we also follow some stochastic differential equations. The distribution of xt is denoted by mu t. And at each point, xt is updated by this stochastic differential equation. Okay, so this term is a little bit different from gradient Rangman dynamics. In a gradient Rangman dynamics, this term was just a nabla L, just a gradient of the objective function. Here, L is replaced by del f over del mu. Okay, so del f over del mu. So what is this? This is called the first order variations. This is a kind of infinite dimensional functional derivative of the functional f. The first order derivative is formally defined by like this. Yeah, this is just a infinite dimensional derivative. So yeah, that's okay. So And so as a special case, let us consider ground transform dynamics. The ground transform dynamics, if mu was just the expectation of L, like this, its first order derivative is just L. The first order derivative is a function. So yeah, the first order derivative of this integral is just L, because this is just a linear functional. So taking a derivative, you have a L as a derivative. So, and you can see that, so in this case, so this term is L. So this is just a ground transform dynamics as I showed in the previous slide. So you can notice that mean field Langevin is a direct extension of ground transform dynamics to the nonlinear situation. Yeah. Okay. So, but the difficult part is that inside this, to evaluate these ones, you should maintain the distribution of the mu t, so distribution of xt in mu t. So you should trace the distribution of mu t. So therefore, to implement this precisely, you should take infinitely many neurons, infinitely many particles, and each particle is updated by this stochastic differential equation. And you should trace the distribution of the xt by looking at the distribution of the infinitely many particles. So yes, that's a bit difficult. But now in the theory, it is defined by like this. Okay, so actually this mean field Langevin can be written like this for to obtain the two-layer neural network. So this is very similar to the vanilla ground Langevin dynamics to optimize two-layer network. So fxk, the finite width network, is just replaced by f mu k. So that's it. So this is almost the same as just a noisy ground descent to optimize two-layer neural network. So this is a nabla f over nabla over del f over del mu. Yeah. So then the next question is the convergence. Okay. to show the convergence, the proximal Gibbs measure is very important. So this is a little bit difficult notions, but I am to explain a little bit. So okay. So to deal with this nonlinear objective function is very difficult. So we take its derivative. So first we take the first order variations. Then we linearize this objective function like this. This is reduced to the original ground Langevin dynamics. The proximal Gibbs measure is the minimizer of this objective function. So okay, so at each point we linearize the objective function, then we have a kind of a localized ground Langevin dynamics. And its spatial distribution is denoted by proximal Gibbs measure. This measure is given by exponential of minus some constant times del f over del mu. So first order variation is coming here. So for the ground Langevin dynamics setting, so this part is just Lx. So yeah, so you see that P mu is mu star, the global optimal solutions. But for the nonlinear case, P mu is not necessarily mu star. So you can say that this is a kind of a tentative of optimizers. So we try to converge to P mu. So this is our kind of a tentative target. Okay, so then to show the convergence, there is an interesting relationship, so-called entropy sandwich. The KL divergence between the mu and the mu star is bounded by KL divergence between mu and P mu, the proximal Gibbs measure. So if we can show the mu converges to the P mu, then it also shows that mu t converges to the global optimal solution mu star. So this is a very important result. So I skip the duality. So okay, then the convergence rate. So please remember that in a grounded Langevin dynamics, if the stationary distribution mu star satisfies the log sovereign inequality, so then we have an exponential convergence. But now in a mean field Langevin settings, if the proximal Gibbs measure P mu t satisfies the log sovereign inequality for all t, we have an exponential convergence. So this statement includes the convergence of grounded Langevin dynamics as a special case. So, but this is the direct extension to nonlinear case. Yeah. So if they're all for any time t, so P mu t, the proximal Gibbs measure satisfies the log sovereign inequality, you have an exponential convergence. So this is very much analogous to PL condition in the optimization literature. So, what is the PL condition? If PL condition was given by like this, if fx minus fx star is bounded by the square of nabla fx, the square of the gradient of fx, so then we say it satisfies the PL conditions. So this is a little bit weaker condition than the strongly convex objective function. Under the PL conditions, we show the gradient arrangement, gradient descent can converge in exponential orders, so linear orders. So the same thing is happening here. So this is actually a PL condition in a Wasserstein metric space part. So you can see that particularly here. So remember that the KL divergence is expectation of a log density ratio. And the Fisher divergence is the expectation of a square of the nabla log density ratio. So you can see some analogous to the PL conditions. So here is F, here is a square of nabla F. So yeah, you see something similar to PL condition. Actually, this corresponds to PL condition in the measure space. Then we have exponential convergence. So we don't have a strong convexity in a Wasserstein space. We don't have any displacement strong convexity, but under the PL conditions, we have an exponential convergence. So yeah, so then when this log sovereign inequality is satisfied, so here's one situation. So remember that. So what we want to optimize is this objective functions, loss function plus regular zero term. So then the proximal Gibbs measure corresponding to this objective function is like this. So if you calculate the first order variation, the first term is just a derivative of loss function, and the second part is just x squared, because the expectation of x squared, so this is a regression term, this derivative, the function derivative is just x squared. So this is a strongly convex functions. So actually, this connects to the Gaussian distributions. So if there is no loss functions, if there's only the x squared, then you have a log sovereign inequality by Berkeley-Emery criterion. So, but there is a loss functions. But if the loss function is bounded, so you have a log sovereign inequality. If the loss is bounded, like yeah, so like a logic loss or something like that, and neural network is bounded, like hyperbolic tangent activations, then you get a log sovereign inequality. Then you have an exponential convergence. But so unfortunately, there is an exponential to minus 1 over lambda 2. So there is no free lunch. But anyway, so we can show the convergence to the global solution. And actually, so if the F has some flat local minima, so the global optimal is flat, so then the solution likely to stay the flat local minimum. Okay, so yeah, so as I said, the mean field arrangement is trying to minimize a complex function. It can be applied to some non-parametric things, de-estimation or a variation inference, but yeah, so I skip these kind of things. And moreover, so you can discretize the dynamics, like instead of infinite widths to finite widths, and you can discretize the time. So behind these theorems, there is some difficult problem, which is called the propagation of chaos. Propagation of chaos is a very difficult open problem in the probability theories. So yeah, so it is a very difficult problem. So okay, so we want to approximate infinite many particles, infinite width network by a finite width network. But to evaluate such a approximation error is difficult because there is a so-called propagation chaos problem. So actually, if you naively apply a kind of a Gromov inequality, so such a finite particle approximator which grows up in exponential time to time t. So that is a very difficult problem. However, in this case, in this neural network optimized settings, we can get rid of exponential t. Yeah. So this is thanks to something like a uniform log sovereign inequality. So we have a kind of a uniform bound with to the particular approximation. But I don't go much into the details here. Okay. Oh, sorry, time is already. Okay, so I want to say something on generalization error, so that I want to finish that. Okay. Okay, so far I have talked about the optimizations. Then the next question is about the generalization errors. Okay, let us consider some classification task like this. So input Z, if Z is a dimensional vectors, and if Z is in a set of A, then the label is Y. If Z is outside of A, so the label is -1. So this is +-1. It's just a it is just a binary classification task with no label flipping. Okay, to train this binary classification task, so we use a mean field arrangement. So suppose that you use a mean field arrangement with a logistic loss, something like that. And in particular, let us consider very specific settings, so-called case sparse parity problem. Okay, so in which Z is distributed on the uniform distribution on a unit cube, the uniform distribution on a vertex of the unit cube. And the output Y is the K parity of Z. That means that the product of Zj from J equal 1 to K. You pick up only the first K component and you take the product. So the XOR is a special case where K equal 2. So K parity situation is a problem. So now we try to solve this K parity problem by mean field arrangements. Then, so I skip some details. So as a result, we can show that the test error, the test classification error can be bounded by D over N. So now we assume the K is a constant. So I'm dealing with the K as a constant. Then test error becomes like a D over N. And moreover, if the sample size N is larger than D square, then the test error can be bounded by exponential 2 minus N over D square. So that means that if the sample size N is larger than D square, you also have an exponential components of the test errors. So this particularly shows that the neural network is powerful in terms of the sample complexity. So now I want to compare this sample complexity with the kernel method. For example, if you use a neural tangent kernel regime, so the neural tangent kernel, then the required sample complexity is lower bounded by the D to the power of K, D to the power of K. So, okay, so if K is greater than 3 or 4 or 5, so then the D to the K is huge. But the neural network only requires sample size N is just order D. So this is a huge difference. So in a very high dimensional settings, so the neural network can outperform the kernel method, like this. Yeah, so but there's some computational statistical trade-offs. Actually, in the mean field arrangements, we can show the exponential convergence, but the constant behind the rate of convergence is very large. So then I cannot say that mean field arrangement is very efficient. So yeah, so there should be much room to improve. Actually, so there is a so-called CSQ lower bound. So the people around the Princeton and New York University are working on this problem very hard. And also the Abe, so from EPFL, so he's also working on very hard on this problem. Yeah, so there's some interesting thing is happening in this year and last years. But yeah, so if you are interested in, please look at this slides. But I skip here. Okay, so as a summary, so I overviewed the representation ability of a neural network and optimization ability of a neural network. So in every situation, adaptivity of a neural network is very important. So in a neural network, you can train the postulates parameters. It induces adaptivity. So then it can improve the statistical complexities. So as for the optimizations, so I mainly showed some convergence of the mean field arrangements. Yeah, but anyway, so through these kind of theories, so I hope we can make the deep learning more controllable. So then by using such a theoretical insight, we want to go beyond the deep learning. Okay, so thank you very much.